Okay, so welcome back. And today, what we're gonna do is to put some hands on practice into the concepts in general that we have studied under logical reasoning. And the language that we'll be using is the one whose interpreter you see at the other half, which is a prologue. Now, in terms of algorithms where I am more interested, the language uses backward chaining, and that should not be any surprise, to be honest, because backward chaining is goal oriented, and because it's goal oriented, I can find out better what substitutions and intelligent techniques, heuristics to use. The other way around is, of course, that backward chaining is nothing but a fancy way of saying backtracking. And backtracking is memory efficient, so resolution forward chaining will do so many facts, they'll find out and they'll just keep adding it to the knowledge base, and I'll run out of memory probably. Backward chaining will be more efficient on that. Now, it's a good time to say that I did not solve the complete logical reasoning problem, and therefore Prolog makes assumption. So two symbols in interpretation will not point to the same object. That's assumed in Prolog. It's a unique name assumption. Every symbol over here, it points to a unique object in the interpretation. I had this problem: best friend of best friend of best friend of best friend of X, infinite object. I'll assume that doesn't happen. I will, in short, say that there is a database semantics assumptions hold. And more importantly, I will say that my model is assumed to be closed world. When I say it's assumed to be closed world, it means that honest R1, comma AI, if I cannot prove it to be true, it's assumed it's false. If I cannot assume R1 is honest in AI, its value is true, it's assumed to be false. I say everything is interpretable, everything's truthness can be found out. If I cannot prove it to be true, it's obviously false, which is unlike open world assumption, where I say that honest R1, comma AI, it could be true. I have evidences to prove that it's true. It could be false. I have evidences to prove that R1 is dishonest. Or it could be, I don't know. I have neither evidences to prove it's honest or evidences to prove it's dishonest. That's an open world. This one is closed world. So anything which cannot be proven to be true is assumed that it's false. I'll also say that I don't do occur check. So no occur check, which means if I unify X with best friend of X, it will pass. There is no occur check. Occur check used to have a lot of trouble, so just get rid of it. Although Prolog has to be completely logical, symbolic, declarative, however, I would assume some support for arithmetics. We will look at that. If there's no arithmetics, we people hate it. There could be some side effects where you read from a file and write to a file. So, and that can affect what it does. With all this, we will try to see if we can do some interesting problem solving using Prolog. So let's get started. I personally love graphs, so let me draw a random graph and let's do search on this graph. What's what's the smallest graph I can make? Maybe just a D and a E. And I just connect this with the least number of edges. Doesn't matter what you take as graph. Let me just represent this graph in Prolog. So I say A comma B is a edge and a full stop. So a dot means that I am telling my knowledge based reasoning system a fact. So A to B is a edge. I know that. I'm telling it. So there's a dot. When I query, I'll not put a dot. That means I'm asking. So a statement which ends with a dot is a tell, which does not end with a dot is a ask. That's how we differentiate between am I telling a fact or am I asking it. So let's very quickly go and add more edges. There's an edge from B to C. There is also an edge from A to C. There is also an edge from B to D. There is also an edge from C to E. And there is an edge from D to E. So these are the edges, and it's a closed world assumption. I did not say there is no edge from B to A. If I don't say, it's assumed to be false. Closed world assumption. Otherwise, if it was open world assumption, I would have said there is no edge from B to A as well. Let's ask something. Is there an edge from A to B? Yes, there's an edge from A to B. However, is there an edge from B to C? Let's find out. Yes, there's also an edge from B to C. Is there an edge from B to A? Let's find out. No, absolutely correct. There is no edge from B to A. The edge from A to B does not imply an edge from B to A. It is a directed graph. Let's get fancy and try substitution. Is there an edge from A to any variable x? So it's like asking that I'm asking, does there exist an x such that there is an edge from A to a variable x? Now, it's Prolog. Anything which starts off with a small case is a symbol. And anything which starts off with a capital case is a variable. So there's no other way to say something is a variable or a symbol. So it's not C++, where if it's int x, x is a variable. So let's find out. Yes, there is a edge from, there is one such edge such that there is an edge from A to x. And I also get the substitution. There is an edge from A to B. Yes, there's an edge from A to B. Are there more answers? Yes, X to C. There is also an edge from A to C. There are two substitutions that Prolog could find out. And luckily they are correct. There are two substitutions, A to B, A to C. Let's do it the other way around. So, is there an edge from any general X to C? And let's find out. Yes, B to C is an edge. B to C is an edge. Are there more answers? A to C is also an edge. A to C is also an edge. I think that's correct. Is there an edge from A to X? And simultaneously, is there an edge from X to D? So, comma in Prolog is nothing but and. So, what this statement really is, does there exist x such that there is a edge from A to X and there is an edge from X to D? Let's find out. So, yes, that's true. There's an edge from A to X is equal to B and then from B to D. A to B, B to D. Are there more answers? False, sorry. There are no more answers. That's all. There are no more answers. Now let's get into, we are trying to do a graph search. So let's write it down. I need to write down a function, say, does there exist a path from a source to a goal, graphically defined as this. And of course, what we'll be doing is divide and conquer recursive function calling. So I'll break this problem into two parts. Is there a edge from S to some X and a path from X to G? So S to X, this is my smaller problem or my unit problem, and a path from X to G. So we all know how to do that in C using recursion. So let's write it down as a definition in Prolog. So I say if there is a edge from S to X and there is a path from X to G, it implies that there is a path from S to G. What did I forget? The base condition. So there exists one such X, and let's add the base condition as well. So my base condition is if there is a direct edge from S to G, and let this be all. So it's this little thing that comes in around over here and this or. So it's read as that if there is a direct edge from S to G, base condition, smallest problem, or there exists an X variable such that there is an edge from S to X and a path from X to G, it implies that there is a path from X to G. You can also use a double implies if you want, but for our case, we don't need it. What I'll do in Prolog is I'll define it exactly the opposite way. So the consequent will come first and the antecedent will come second. Why? I absolutely have no idea. But the consequent will come first and the antecedent will come next. So it will be given as path S comma G. If there is a edge S comma G, or there exists X such that there is a edge from S to X and a path from X to G. And in Prolog, we will have and as a comma. X is not written. It's obvious there exists an X, and or is either a semicolon, or instead of writing a semicolon, because the statements can become too long, sometimes you redefine it up. And the implies by will become colon dash. That's Prolog. So let's write this definition down real quick. So I say a path exists from S to G if there is a edge from S to G. Make sure the specifics come first. And I'm not using the semicolon, so I'll have to write it down again. If there is a edge from S to X and there is a path from X to G. And both end with a dot because it's a fact. I am telling out this to the system. So let's check this little thing up. Is there a path from A to B? Is there a path from A to B? I'm asking, so no dot. Yes, there is a path from A to B, and that's the only answer possible. Just one. The last falsehood means nothing more. Is there a path from A to C? Yes, there is a path from A to C. It could get 1, 2, 2. I mean, the two truths is that it could get two paths from A to C. One is ABC and the other is direct AC. Backtracking, it will give you as many answers as you want. Is there a path from A to D? Yes. And is there a path from A to E? Yes, again. Let's do it the other way around. Is there a path from B to A? B to A, yes, there is a path. Is there a path from C to B? False. There is no path from C to B. And like this, I could do it for any number. Now, let's do one thing. A and B is same as B and A. So A and B is same as B and A. It shouldn't make a difference, does it? Absolutely no. I just changed the order of and. Does it? C to B. And oops, what happened? My language was declarative. A and B is same as B and A. I just changed the order. It gives me stack limit exceeded. So now that we haven't applied this as a black box library, we have actually studied that up. Let's see what happened. So my query is there a path from C to B? And what do I do is that there's no edge from the two of them up. So of course I will break it up. Is there a path from C to some X and simultaneously a path from an edge from X to B? No substitution will make that true, so I'll have to go in again. Is there a path from C to X1 and simultaneously a path from edge from X1 to X? So can I get X and X1 such that this holds true? It turns out it will not hold good, and what you'll end up doing is that you'll end up in an infinite loop. Earlier what was happening is it was forcing this thing first. So it would only return X as substitution such that XB is an edge. So earlier this was getting solved first, and based on the X returned, it was doing a substitution here. And of course it's an and or graph search, we've already seen that. So by binding itself to a value first, by ensuring this is true first, our X's got highly limited, and because of that, the X's getting limited, the search could, in a finite amount of time, return a false. Now it's an infinite loop. It doesn't know, because it doesn't know how deep it needs to try with all these X's and X1s. And therefore we try doing the specifics first before the generic, because the recursive call comes at the end so that my X's could be fixed and passed into here, rather than my recursive function trying to decide what all combinations of X's are possible. And that's a little procedural trick that we have added around over here. So this works. We've seen this to work. Let me add in a new edge. It should make a difference. And let's add E and B. So I only need to add one more edge, E and B. So now is there a path from A to D? Absolutely correct. There is a path. Are there more paths? Yes, there are more paths. There are many paths. Of course, backtracking, you'll end up in this cycle. You'll return ABD, you'll return ABCEBD, and then ABCEBCEBD. So you know how to backtrack a path without that visited, without that closed. So you'll get lots and lots of paths. Let's try the other way around. Is there a path now from B to A? Okay, so it does end up in something weird. Now it's an infinite loop, of course. It's trying to generate all the paths possible so as to get to A. Using my eyes, I can say by common sense there is no path from B to A, but Prolog has to generate all the paths possible. and the number of paths possible for a graph with cycles is infinity. And how do I solve that up? So far we were doing a DFS. Now, of course, we know the answer is a depth first search, which is pre-implemented because it's a backward chaining with a closed or a visited. So my problem is that backtracking in a graph with cycles is infinite. My solution is, of course, now depending upon what do you call it, I call it as a closed and some people call it as a visited, whichever you prefer to call it. That's only thing that I need to add. So let's add that up. And because visited will be a list, so now is the first time that I will have to tell you how to deal with lists in Prolog.